Hello, it is final season. So here we're going to be looking at trying to help somebody get ready for their calculus final by looking at some problems on a worksheet and trying to describe what to do and hopefully why in some cases as much as I can. I keep getting interrupted, so I'm going to try to make this as quickly, or I'm going to try to get through this as quickly as possible to hopefully not get interrupted again. All right, so we've got the first one we're going to start with number 3. It says identify the intervals of concavity and inflection points for the function, and then we have a function right here. And so I'm going to explain this by looking at a graph real quick. So looking at this graph, what we're talking about is where this graph opens down, where this graph opens up, then where it opens down again, and we got to figure out where it stops opening down and starts opening up. And the last part too. So we do that by we're talking about the slope of this line. Okay, so the slope is positive to this point, then it's negative, then it's positive again. So we want to know where this slope stops getting steeper and starts heading back up toward being positive again. All right, so to talk about the slope in the first place, we got to talk about the derivative. Okay, so right here I've graphed in green the derivative of the function. So everywhere the derivative is positive, so everywhere the green line is above 0, the slope of the original line is positive. Everywhere the slope is, or the derivative is below the x-axis, where it's negative, the value of the slope of my original function is negative. So basically I'm looking for this point right here where my slope stops getting steeper in the negative direction and starts going back towards 0. So I'm looking for that point right there. That's called my point of inflection. Now using this software I can actually see what my values are for those points, but I'm pretty sure the expectation is that we can find those algebraically. And so in order to do that, we've got to find the relative min for our derivative, which means we're going to have to take the derivative of the derivative, or the second derivative of our original function. All right, and we want to know where the relative min and max are for our first derivative, so we're looking for where our second derivative is equal to 0. Okay, so let's talk about how to do this algebraically. All right, I've already spelled it all out here. I'm just going to be talking about what I did in each part. So to go from the first part to the first derivative, I'm going to be using the sum and difference rules for differentiation, which basically says that if you've got several functions added together, you can find the derivative of them by taking the derivative of each individual part and then adding or subtracting them however it was to begin with. All right, and so I'd combine that with what's known as the power rule, where you take your exponent and multiply it by your coefficient and then decrease the exponent by 1. Okay, and so that's how I went from here to here and then from there to there. So now that we got the second derivative algebraically, we want to know where that's equal to 0, so we set it equal to 0. Luckily this is just a quadratic equation, so then you can solve it however you want to solve quadratic equations. You could do the quadratic formula if you wanted to. I just factored and I got my two x values for my inflection points. X equals 2 and x equals negative 1. Now these are just the x values for the inflection point. To find the points themselves, you have to plug these values back in to your original equation up there. Alright, so I got to plug them back in up there. I didn't do that. I'll leave you to do that because that's not too bad. Okay. Now we need to figure out where it's concave down and concave up based on just what we're given. And the way we do that, the way I like to do it, is to set up a number table or a number line and mark it like this, where it's concave down and concave up. So if I didn't already know where it was, though, what I would do is I would find a value in here and plug it back in to my second derivative. So I like 0. If 0 is not one of my inflection points, I use it. And then since I know it alternates between concave up and concave down, I can figure out the other two once I know any of them. Alright, so plugging in 0 into my second derivative gives me the value of 12. which is positive, so I know it's concave up between -1 and 2. And so I know it's concave down below -1 and concave down above 2. And whatever kind of interval notation you want to use for that, go for it. All right. Next, we have some integrals. Now the directions for this one was to evaluate the integral by substitution. They give you that by substitution to kind of lead you in the right direction and help you. So basically, when we're doing integration by substitution, we're undoing the chain rule. So we need to figure out our secondary function and its derivative, and then make sure that's in our original equation, and then we can integrate it to get our final answer, which is going to be the integral of the whole function with our subfunction inside plus some constant. All right, so this first equation right here, that 3 minus 5x stands out to me as a good candidate for substitution. So I'm going to set it as u, because I do what's called u substitution. Okay, well then I find the derivative of that, and I get that the derivative of 3 minus 5x is -5 dx. Okay, now I just used the same thing as we used on the previous problem, your power rule and your well, actually it's subtraction rule in this one, to find that. Now the only issue that I have now is that my original problem doesn't have a -5 dx in it. It just has dx. Okay, so I need to put in a -5, but I can't just multiply by -5. That would change the value. So I also have to divide by -5 as well, which is the same thing as multiplying by 1 over -5. Okay, so now that I have it set up, I can substitute in. I only come up with one more issue though. When I substitute, I'm not talking about x's anymore. I'm talking about u's. Okay, so I have to change my lower and upper bounds from x's to u's. All right, so how I do that is I take my equation that relates u to x, and I plug in my bounds. So when I plug in 1 for x, I get 3 minus 5, and that gives me -2. When I plug in 2 for x, that gives me 3 minus 10, which is -7. So now that I've substituted, I've got my integral here. It's 1 over -5 times the integral from -7 to -2 of du over u squared. Now, I want to use my power rule, so I went ahead and rewrote that du over u squared as u to the -2 power times du. Okay, so then what I'm going to do now is integrate. The way you do that is the opposite of our derivative. So if we were thinking about this as going from our derivative to the original, when we found the derivative, we multiplied by the exponent, then we subtracted 1 from it. So what I've got to do now is I've got to subtract 1 and divide. Add 1 and divide, sorry. Add 1 and then divide by that value. So -2 plus 1 is -1, so I divide by it. And then I want to add 1 to my exponent to get back to the value that it would have been. So I got u to the -1. Once again, I'm going to get rid of my negative exponents. And so anytime you divide by -1, the whole thing changes sign. So that's where I got this -1 over u from. So now we are just evaluating from -7 to -2 of this value and multiplying that by -1/5. And I did that right here. So I plugged in -7 for u. I got -1/5 times -1 over -7 minus, and then I plug in the -2. So we get -1 over -2. All right, and that's a lot of negatives. If we evaluated that, we would end up with 1/7 minus 1/2. And that's where I got the -5/14 from. Then you do some computation, and you get your final answer finally of 1/14. All right. Whew. Next one. Here we have, I've got both of them up, just ignore the bottom part. The second one is pretty straightforward. So I let the natural log of x be my u value, because the derivative of the natural log of x is 1 over x dx. And looking at this, it's just u times du. Okay, so whenever I take the, almost forgot, you also have to remember to change your upper and lower bounds by plugging in your original bounds to the equation that relates u and x, and that's where I got that 0 and 1 from. So now I just find the integral of this value, and I get 1/2 u squared, and I evaluate that from 0 to 1, and so I plug in 1 for u, and I get 1/2, plug in 0 for u, and I get 0, subtract the 2, and you get 1/2. Alright, this last one is a indefinite integral. We're not given any bounds. And we've got r times e to the 5r squared dr. So here, I'll let the 5r squared be my u value of u. And so whenever I find the derivative of that, 2 times 5 is 10, and then subtract 1, I get 1. So that's where I get the 10r. I forgot to put my dx in there, or dr in there. So let me just do that now. dr. All right. And so I also forgot it right here. All right. And so whenever we're doing this, once again, I don't have 10r. I only have an r. So in order to get that 10r, I have to also divide by 10. So I want to multiply by 10 to have my value of, or my derivative of my u. And so I have to divide by 10 as well. Alright, so now I can do my substitution. I substitute in u for 5r squared and du for 10r dr. And then from there, I finish the problem. The integral of e to anything is just e to whatever it was. So I take the integral, then I plug in my value for u again, and I get 1/10 e to the 5r squared plus some constant. Alright, I hope this helps so far. I'll try to post a video later on if it does. Have a good one.